The third case study is about coalescence of small water droplets. Very small water droplets, that is several hundred water molecules, have very large surface area per one water molecule. If two such droplets merge, that is coalesce, the surface area decreases and the surface energy is transformed into heat, and we can study this phenomenon by simulation. Such phenomena are important for studying nucleation, asphalt ripening, and so on. If droplets get warmer, they have a tendency to evaporate some water molecules and cool down again. For the simulation, we will use the SPCE water model and the standard setup, that is Verley integrator, shake to maintain bond length of water molecules constant, the balance and thermostat, and quite cheap smooth electrostatics, which is cutoff and 12 angstrom. The steps will be: first we need to prepare such a droplet. So first we will prepare a box, a periodic box, because it's easy, and then this configuration will be placed into a larger box. So instead of box by surface forces, soon from a cube we'll get something spherical, so that in this case we prepare a spherical drop. This configuration will be replicated twice, and both droplets will get certain small velocity together. This will be simulated at constant energy, that is in the microchemical ensemble at this moment without the thermostat, that is if we turned off for this, and we'll see what's happening. Of course, this increase in temperature can be calculated also theoretically. So let's use 300 water molecules, temperature let be 270. This water will not freeze. And let's start. And what we are getting is just cube. It's not necessary to be terribly well equilibrated, because we will continue. The next step will be to prepare this droplet. There are a few technical inputs here, how to manage this, but it's better just to have a look what happened. That is, a cube from the previous simulation was put into a larger cube. So what we got is here. This is the starting point of this step of the simulation, and step by step this cube made something which is pretty spherical. Okay, so let's have a look at the convergence profiles. We can see that the potential energy decreased, so at this moment it can be considered as equilibrated. The temperature is about the 270 that was set at start. Now we will replicate this into a bigger simulation cell, which is not cubical, and what we can do is to watch what's happening during the simulation, because this simulation will be longer. So what we can see here, this is a starting configuration, and by a picosecond we can see what's going on. And now I will stop recording, because it's gonna take, let us say, a minute or two, and we'll continue shortly. Well, the simulation has finished, so let's show the trajectory again. And let's show the convergence profiles. So I will enlarge them to the full screen. And this is the total energy, the sum of the potential and kinetic energies. We can see small decrease at the beginning, and then it's essentially constant. Well, it's not fully constant, but you can see that the error in the constant energy is at the 5th decimal digit, so it's considered as a practical constant. Here we have the potential energy. It decreases a bit, and we are mostly interested in temperature. And we have here 3 curves. The white curve corresponds to the total kinetic energy, that is rotational and translational. The yellow curve corresponds to the rotational temperature, and the cyan curve corresponds to the translational temperature. We can see at the beginning some bit scattering, and it is likely caused by the initial configuration, because we took 2 droplets that were equilibrated at 270 Kelvin, but they were quite close together, so that there was certain attraction here, and also they were given small velocity so that they could collide later, and that's why we have here such small increase. Then it's essentially around 275 the temperature, and then it decreases a bit after a small period of time. Thank you for your attention.